In this video, we'll see the working of a CS amplifier using LT-Spice simulation tool. So this is a CS amplifier, common source amplifier. Specification what we are looking at is the amplifier should have a gain of 10 volt per volt, and we are making some assumptions. So the drain current should be let us assume it as 1 milliampere, and we'll assume the supply voltage we read as 1.8. Let the threshold voltage of the MOSFET be 0.4 volts, and let us assume that mu n into Cox is that is Kp is equal to 100 microampere per volt square. So let us assume that Vgs is equal to 0.6. So using the design equation, that Id is equal to half mu n Cox, which is nothing but Kp into W by L Vgs minus Vth whole square, which is the expression for drain current in saturation mode. uh, why we are chosen this equation is because the MOSFET will be operating in saturation region when it is used as an amplifier. So we end up with using this equation, the W by L happens to be 500. So let us assume the value of L to be 10 micron, and let us assume the value of W to be 510 micron, that is 5000 micrometer. So let us see what is a circuit diagram to realize the CS amplifier. So we have this circuit diagram where there is a MOSFET which is N MOSFET, and there is a drain resistor which is connected. There is a R1, R2 which will provide the required biasing, and we have a coupling capacitor of 0.1 microfarad which will going to couple the input voltage to the amplifier, and will measure the output voltage at the drain point. So so at this particular node we can write the expression for VGS as, because VGS is nothing but the voltage at gate with respect to the source, which is now given by VDD into R2 by R1 plus R2. So in this equation we know what is VGS, that is 0.6 volts. That's what our assumption is. And since we have only one equation and we have two unknowns, that is R1 as well as R2, we know also VDD, which is nothing but 1.2 volts, so which we have assumed. So by substituting those values and assuming the value of R2 to be 100 kilo ohms, we end up with the value of R1 as 200 kilo ohms. So we shall see the small signal AC equivalent model. So this is written by grounding the DC voltage source, by replacing the capacitor by the short circuit, and replacing the MOSFET by its AC equivalent model. So we can rewrite this AC signal model as so and so, that is R1 R2 in parallel, and this is the small signal voltage, and V0 is measured at the drain with respect to source, and this is the expression for V0 which we have derived in the class, and we know that the gain happens to be uh, which is 10 here. So now this is minus GM into RD should be equal to minus 10. So now here GM is also unknown. So here we know the value of this as 10, and this is GM. We don't know what is the value of RD. We don't know both the values. So let us use the equation of GM and try to get the expression for. I can see. So this is the expression for GM in terms of ID, mu and Cox, and W by L. Because we know the value of ID, we know what is Kp, we know what W by L. So GM happens to be, that is transconductance of the MOSFET happens to be 10 milli ohm inverse or 10 millisiemens. So by knowing the value of GM, by knowing the value of AV, we can estimate what is the value of RD. Now RD happens to be now 1 kilo ohm. Now this way, so we can get all the required resistor values for the circuit. So we know what is the value of R1, R2, RD. R1, R2 are used to get the required VGS, which will give the required drain current of 1 milliampere, and RD is used to, or the value of RD is selected such that we're going to get a gain of 10 using the equation. So let us find out, okay, what are the values of the different resistors. R1 is 200k, R2 is 100k, we have RD is equal to 1 kilo ohm. This is coupling capacitor. Kp is the transconductance parameter of the MOSFET, which is 100 microampere per volt square, threshold voltage 0.4, the width of the transistor is 5000 micron, L is equal to 10 micron. So with these values we shall do the simulation. So we shall go back to LT Spice. Now this is the exact circuit what we are looking at. So I have applied an input voltage which is sine wave, and the same R1 R2 whatever we designed is being collected. Now first of all let me do the dot op, which will give the DC conditions. If I run this now, so let us verify what is the voltage that is at the gate and what is the drain current that is flowing. Let us also verify that whether this MOSFET is in saturation or not. So let me run this. Upon running we have these parameters. So this is 0.8 and this is NF 002, which is this NF 002. Okay, how we are getting this as 0.8? Actually this 0.8 volts corresponds to the drain. So this 0. So let me just verify what are the. Now at this point of time, okay, you are unable to understand what is this 0.8, 0.6 and 1.8. Let us name the nodes as gate, drain and source. So then we'll just see, okay, what are these voltages. So let me just label them and then we will just come back to this .op command again. I can see I have labeled this as gate, this as drain. So let us see what is the .op will give us. Now you can see the V drain. Whenever it is V drain, the other terminal happens to be the ground. So between ground and drain, so in this case ground is nothing but the source. So between gate and source I have 0.8 volts. Between gate and the source, this is between gate and the drain. So this V drain happens to be 0.8. Between gate and the source it is 0.6, and this 1.8 happens to be the supply voltage. You can see what is the drain current. So drain current is actually 0.01 ampere, which is 1 milliampere. So that's what our design. So in our assumption we thought that, okay, let us design an CS amplifier for a drain current of 1 milliampere. So 1 milliampere is flowing, and we can see now the gate voltage is 0.6, the threshold voltage is 0.4, and VDS at is 0.2 volts. Since the drain to source voltage is 0.8, the MOSFET is well in saturation region. So let me apply this sine wave and try to see what is the signal we're going to get. So let me change the simulation setup now. So now it should be the transient response. So since, let me see, around few cycles, so let me give it as 1 millisecond. So 1 millisecond will certainly give you, okay, 1 by 20 kilohertz will be far less than 1 millisecond. So I'll get more than 1 cycles. So let it be 0 and let it be 1 microsecond. So let me make it as 1 microsecond. So 1 U. So let me run it now. Upon running, let me just place this. Upon running, so let me see the input voltage, which is a sine wave. Let me see the output voltage also. Now you can see output voltage is uh, clamped at 800 millivolts, because that was the voltage at the drain. So let me just see them in separate panes. So let me just give this input and output in different panes. So let me put this input in the first plane. Now you can see the input voltage is this is 1 millivolt peak, this is minus 1 millivolt. So peak to peak happens to be 2 millivolts. So let us find what is, this is 810, this is 790 millivolts. So here the peak to peak happens to be 20 millivolts. So you can see, so the output peak to peak is 20 millivolt, whereas the input peak to peak is 2 millivolt. So that is 20 millivolt by 2 millivolt happens to be a gain of 10. So this is our output. So at the drain you are taking the output. At the gate side, that is before the capacitor, you apply the input voltage, which is the input. So output by input, that is drain voltage divided by the input waveform at the drain divided by the input voltage before the capacitor. That ratio happens to be 2 now. So this way we can actually get a gain of required value. Now let us change the value of this resistor RC, which is Okay, that is the resistor RD, which is usually connected to the drain. Okay, let me just modify it to RD. Suppose if I change the value of this RD, which is 1 kilo ohm, if I make it 1.2 kilo ohm, so does your drain current change? Now the question is, the change in RD, will it change the drain current or not? So let us change the resistance from 1K to 1.2K, and we'll just again do the dot OP and find out whether the drain current remains as 1 milliampere or not. So let me change. Now you can see I have changed the value of RD from 1K to 1.2K. So let me verify. Of course, I have done this dot OP now. Now I'm not doing the transient. You can see there is a semicolon coming, means okay, this is commented. Now I'll be doing the dot OP. That is, I'll be seeing only the DC current and voltages. If I run it, so it is interesting to see. So what we're going to get. See now the drain current has reduced to 0.6 volts. The gate voltage is still 0.6. This is your VDD. Carefully observe this ID. ID still remains as 1 milliampere. So does it mean that okay, the current has not changed? Yes, the current has not changed. Why the current has not changed is, we know that in the output characteristics of a MOSFET, when the MOSFET is operating in saturation region, the drain current ID is independent of VDS. So in the previous case, the VDS was 0.8, it was 1 milliampere. Now it is 0.6, it is still 1 milliampere. So as long as this is more than 0.2 volts, how do we get the 0.2 volts? Because 0.2 is nothing but VDS sat. So here now VGS is equal to 0.6, so that's what is this gate voltage, and our threshold voltage is 0.4, the difference is 0.2. As long as this remains at 0.2 volts and more than that, so I'm going to get a current of 1 milliampere. So let me just slightly furthermore increase this RD and then again check for the value of ID. Now you can see I have modified the value of RD from 1.2 to 1.5K. You can see the drain current has reduced from 0.6 to 0.3 now. Now you can see still the drain current is 1 milliampere. So why means, okay, this 0.3, whatever you have, 300 millivolts, is certainly greater than VDS sat. So that's why it is still 1 milliampere. Let me further increase this drain current and then, sorry, this RD value, and try to see whether the drain current remains constant or not. So let me stop this and then again find out whether it will going to. Now it is interesting to see when the value of drain resistance RD is increased from 1.5K to 1.7K, the drain voltage is now 161 millivolts, that is 0.161 volts, which is less than the threshold voltage, less than the saturation voltage, VDS sat. So VDS sat is 0.2 volts, now it is less than 0.2. So naturally the drain current is no more 1 milliampere, now it has become 963 microamperes. So this is 963 microampere, which means that now the MOSFET is operating in linear region. So if at all if you want to use this MOSFET as an amplifier, we should always ensure that drain to source voltage is more than the VDS sat. So the value of RD cannot be so high that, so we're going to end up with the MOSFET operating in the linear region. If the MOSFET operates in linear region, we will not get the amplification. Now if we again check the amplification, okay, let us verify whether at this point whether we get the proper amplification or not. Now with this RD as 1.7 kilo ohms, and now the MOSFET is operating in linear region. So with RD as 1.7K, we are supposed to get a gain of 17. So as per our earlier values, if you actually verify the input voltage, output voltage peak to peak by input peak to peak, you can see now hardly there is a difference of the output peak to peak is only 6.4 millivolt, whereas the input peak to peak 2 millivolts. So now 6.4 by 2 happens to be around 3. So we are not getting a gain of 17. So why means, since the MOSFET is operating in linear region. So let us again redo it for 1.5K and then verify whether the gain is 15 or not. Now you can see I have reduced the value of RD to 1.5K. So this 1.5K will ensure a drain to source voltage of 300 millivolts, which is more than 200 millivolts. Now the MOSFET is in saturation. If you actually see the peak to peak of output by peak to peak of input, so it is naturally you can see now this is peak to peak of output is around 30 millivolts. So you can see here it's around 30 millivolts. So the gain is around 15.